Hello, Math Studies students. Welcome to an online lesson. Today we'll be talking about standard deviation and variance. Both of these are a type of dispersion. So we'll talk about what that means. And so we will use technology to find standard deviation and deviation variance and other measures of dispersion for our success criteria. All right, so a big list of terms and notation. Again, you can pause the video if you want to write these down first. Dispersion is the measure of the spread of data. We've already looked at one measure of dispersion already. It's called interquartile range. Obviously, the wider your quartile 3 and your quartile 1 are apart from each other, or the bigger that number is, the more spread out your data is. If we look at, for example, ages of students in one of our math classes, we will find that there's a very small dispersion. You're all within maybe a year of each other. Yet if we look at the dispersion of teachers who teach at our school, you're going to find a much bigger dispersion because the ages are spread out from early 20s all the way to 50s, 60s, and beyond. So when we're measuring dispersion, we can do that a number of different ways. Again, interquartile range is one. Range is another. Range is just a simple measurement. Whenever you see the word range in statistics, we are talking about subtracting. And so interquartile range, we subtract the upper quartile minus the lower quartile. Here, when we talk about regular range, we subtract maximum and minimum values. So there's another measure, a little bit more scientific or mathy, which is called standard deviation. And that measures the deviation between the scores and the mean. So how far away are we from the average? And so that's an interesting measurement that we'll talk about today. The larger the standard the deviation, the more widely the data is spread. So if you have a very small standard deviation, it means most of your data is pretty close together. Standard deviation provides a better measure of the spread of the data than range or IQR because it considers all scores in the data. It's not just looking at the highest and the lowest or, the upper and lower quartiles. It's looking at every single piece of data. But because we're looking at every single piece of data, it's a little bit more involved. And so for ungrouped data, we have this formula S equals the square root of the quantity. And then we've got that funny E looking thing, which is a Greek letter sigma, which we've talked about before, and it means sum of X, which represents any piece of data. So if you have 4 pieces of data, you'd have 4 different pieces or values for X. If you have 100 pieces of data, you'd have 100 different values of X. For each one of those, we would subtract X with a line over it, which we know means mean. We square that data, and then we divide by N, which represents the total number of our data. So if we had, let's say, 4 terms, we would divide by 4 there, and then we square root that whole thing, and that's standard deviation. For group data, we add in a frequency there, and so that if a data is used multiple times, you can multiply that by its frequency. So each piece of data would have a frequency that goes with it, and then you would divide by the sum of the frequency, which is the grand total of all your data. Those formulas look a little bit overwhelming, but I'm going to show you how to use the first one here for the ungrouped data on our next slide. So I have a small set of data here, and I want to show how to find standard deviation. So again, I'm going to write our formula down. S equals, and we've got our sigma, X minus the mean, quantity squared, all over N. We have these 8 numbers here, 3 through 10. And again, we're trying to find standard deviation. So the first thing that we need, if we go inside of our groups here, order of operations would tell us, look for any groups. We have a big radical, and this radical is our first group, but we can go inside that as well. There's a numerator and a denominator. Inside the numerator, you've got this other set of parentheses here. And in order to start inside those parentheses, the first thing we would need is our X, our data. So what I'm going to do is I'm going to make a little table here. And my first column is going to be my data, which is just 3, 4, 5, 6, 7, 8, 9, and 10. For my second column, I'm going to do my data minus the mean, because that's the first thing it tells me to do here. It says take the data minus the mean. In order to do that, I would need to know what the mean is. So to find my mean, I'm going to add up all these numbers, and I've done that ahead of time. But if I add up 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10 and divide those all by our 8 numbers that we have here, we should end up with our mean being 6.5. All right, so now we are going to take our data minus the mean. Well, in this first one, remember our mean is 6.5 always, but our first piece of data was a 3. So we're going to take a 3 minus 6.5, which will equal negative 3.5. Now, I'm not going to show my work for all these, but that's what I'm doing. So the next one, I'm taking 4 minus the mean, which becomes negative 2.5. For the next one, I'm taking 5 minus the mean, which is negative 1.5. Then I'm taking 6 minus the mean, which is negative 0.5. 7 minus the mean, which is just 0.5 or 0.5. And then 1.5 and 2.5 and 3.5. Now there's this nice little pattern that happened here where we have the opposite terms. It starts with a negative 3.5, finishes with its opposite 3.5, so on and so forth. It's sort of a symmetrical pattern, but that's only because my numbers were all in an order. You won't always see that happen. All right, so we have that. Now what happens next? Well, once we've subtracted our data and our mean, we're supposed to square it. So I'm going to make my next column be x minus the mean quantity squared. So I'm just going to square each and every one of these numbers, and I am going to need a calculator to help me out with this. So for the first one, I'm taking 3.5 squared. Which gives me 12.25. 12.25. Then I'm going to take negative 2.5 squared. And I get 6.25. And then 1.5 squared gives me 2.25. 0.5 squared gives me 0.25. Again, the positive versions will be the same. And 2.25 and 6.25, and then finally 12.25. All right, so let's look at what we've done so far. We've taken our data, which was this x in the formula. Then we took that data minus the mean, which is everything inside the parentheses in the formula. Then I took those values and I squared them, which was the whole group of the numerator. And then the next thing I see is sigma. And the sigma says add these up. So I'm going to take all of these values, the 12.25 plus the 6.25 plus the 2.25, so on and so forth, adding them all up, and I get a grand total of 42. And that is dealing with the sum symbol right here. Add up all the data minus the mean squared. And I have 42 now for my standard deviation so far. And then it says take that number. So that's my numerator essentially. All over n, which is the number of terms. And we can see that we had 8 terms here. So 42 divided by 8. And all that's going to be square rooted. And that's equal to my standard deviation. So I could take 42 divided by 8. It doesn't come out to a whole number. It'll be 5 1/4, and then I could square root that. Or I can just do a decimal approximation, or I could leave it as a whole number or as a fraction. I'm sorry, lots of different options. But I'm going to take that number 5.25, and I'm going to square root it. So s equals the square root of 5.25, which is approximately 2.29. So 2.9 is my standard deviation. So that's how you do it by hand. That's what the formula tells us to do. It looks fancy. It's this crazy math speak here, but it's just giving you step-by-steps. And if you break it into its parts, it's very doable. But again, that was just for 8 numbers. What happens if I have 20 numbers, or 100 numbers, or a frequency table where a bunch of numbers repeat, or things like that? So we have another option. Another option is to let the calculator do all the work for us. But I wanted to show you that these numbers weren't just coming from thin air. There's actual math. And again, none of the math goes beyond squaring and square rooting as far as its difficulty. So this is math that I feel like, even a middle schooler could understand. So let's try it now with the technology. I'm going to pull up my digital calculator here. And we're going to go to Stat Edit. And we're going to enter in all of our data. So we go to Edit. I have some stuff in my list, so I'll clear those out. And now I'll just enter in my numbers. 3, 4, 5, 6, 7, 8, 9, and 10. All right, so I've entered in my values. I have no frequencies, so I don't need to put in a list too. And now I'm going to go back to Stat, go to Calculate. Again, because there's no frequency, well, I'll just select my one variable stats. And I could literally just press enter because it's automatically going to go to list 1. But just to be safe, I'll tell the calculator I have list 1. That's my only data, no frequencies, so no commas necessary. If you have the new operating system, for your list, put L1. For your frequency, just put 1 because you only have one of each number. And then we go ahead and press enter. And this gives us our one variable stats. Now you'll notice the mean that I had found earlier of 6.5 is there. You'll also notice the n value. So the mean is right here, 6.5. The n value of 8, meaning there were 8 terms. I used that in my formula as well. Then there's this sigma x, which we did not use. That was not part of my calculation. Sigma x squared, which was similar to what I did, but I did the mean subtracted from the data squared. Then we've got these two values right here, s sub x and sigma. It's a lowercase sigma. Looks like a little cursive O. And those are both versions of standard deviation. If you're taking IB biology, this is the version that you would use for standard deviation. I know you guys use a computer program in that class, but you could just use your calculator as well. For ours, the formula that we just did, we're using a slightly different version than you use in the science class. Again, there's more than one way to do this, and those numbers are very similar, but the one that we want is the sigma. So we never for this class want the SX, we always want the sigma x, which again means standard deviation. And you'll notice 2.29 is the first 3 significant figures here, and that's exactly what we got when I did it by hand as well. So standard deviation, put your data in the calculator, and then go to one variable stats. All right, let's do one last example here. A little bit more term and notation to start with. So one other measure of spread is called variance. And variance is actually the exact same thing as standard deviation, but instead of using S or sigma, we use S squared or sigma squared. Now you'll notice when I did this by hand, my very last step for standard deviation was square rooting. Well, our answer is going to be squared, and so you don't actually have to square root. You can just stop one step earlier if you were doing it by hand. Or if we're doing it on the calculator, variance does not come up. So how you find variance is you take your standard deviation and then you square it. So just read it off the calculator and square it. So here on our last example, I've got a frequency table, 11 through 19 with different frequencies. Let me pull up the calculator again, and we can enter these in together here. We're asked to find the standard deviation and the variance. So stat, edit, list 1, I'm going to clear that list out because I have a whole new set of values. And we're just entering in the numbers one at a time, 12. And again, they're sequential this time, which is nice. 13, 14, 15, 16, 17, 18, and 19 is my last value for my data. Then I've got my frequencies. So 3, 4, 5, 2, 8, 9, 5, 8, and 6. When I'm all said and done, I should have a blank here for the cursor for each one of those lists to show that I have the same number of values. And I'm going to go to Stat, Calculate, one variable stats. This time I have a frequency list. I need to tell it where it is. So I have L1 for my data, and then L2, list 2 for my frequency, separated by a comma here. I press Enter. And now we can see that my standard deviation, again, that we want to use in class here, is not the SX, but rather lowercase sigma x. And to round that to 3 significant figures, I have 2.38. The next digit was a 2, so we keep the 8 as is. And that would be my standard deviation. In class, you can literally just write S equals, lowercase s for standard deviation. If you write sigma, lowercase sigma equals, that's fine as well. But I think most of us would be most comfortable with just an S. So then don't get confused because we don't want to use the S on the calculator. We want to use the lowercase sigma. Now to find the variance, we're going to take that number and square it. So we had 2.38, and I might even go one digit past that because if I'm going to square it, I'm not using the 2.38 as a final answer. So I'm going to take 2.382, go one digit past. So if I go 2.382, and then square that value, I get approximately 5.67, and that would be my variance. So our second step was to find variance, and 5.67 would be my variance. Again, just the standard deviation squared, but since we're using a rounded answer, I made it a little bit more accurate. All right, that is our lesson for today. On page 199 and 201, you'll find some problems dealing with this. And you're going to want to be using your technology here. You don't have to solve these by hand. You don't have to do it the long way. But again, I encourage you to maybe try it out so that you sort of see how that all relates and see if you get the same answers. But technology is our main goal.